This lesson, we're going to learn how to develop the differentiation rules. So why do we need to develop the differentiation rules? It's because when we are computing derivatives from first principle, it's tedious and time-consuming. Therefore, we will develop differentiation rules by using the first principles to simplify the process of differentiation. The first rule we are going to generate is called the constant rule. Given the original function fx equals c, which means fx is a horizontal line, then the slope of a tangent at any point on this horizontal line will be 0. That means f prime x equals 0. And there is another way to write these rules. So fx equals c, I can write as y equals to c. So f prime equals to 0, I can write y prime equals to 0. And y prime, there's a different way to write it, is using Leibniz notation, which is called dy over dx equals 0. This means the slope of a tangent, which is rise over run, which is the changing y over changing x. That's why we say dy over dx. But since y is c, so we can write d over dx and differentiate the function, we say c equals 0. So we say this is the Leibniz notation. All right, let's do the proof. F prime, which is your slope of a tangent, equals the limit h is approaching to 0, f of x plus h minus f of x divided by h. And let's find out what will be f of x plus h on the side. So we know fx equals to c. Then f of x plus h will be c. So we say c minus c over h, which is limit h is approaching to 0, 0 divided by h, and we know 0 divided by anything will be 0. Therefore, we say if fx equals to c, then f prime, which is slope of tangent, will be 0. As you can see from the proof, slope will be 0. As a side note, let's explain this. What does it mean by f of x plus h equals c as well? So if we have a function fx equals to x plus 2, then when f of 3, you will say that's 3 plus 2. F at 5, you will say that's 5 plus 2. So f at a, you will say a plus 2. Then f of x plus h, you will say that's x plus h plus 2. But right now, in our fx function, there's only a constant c. That means there's only a 2. So if there's no x here, then fx equals to 2. Then f at 3 will be 2. That means f at 5 will be 2. And f at a will be 2. So f of x plus h will also be 2. That means if fx equals to c, which is a constant 2, then f of x plus h will be 2. And if you look at this graph here, so that's x-axis, that's y-axis, there is a function y equals to 2, which is fx equals to 2. This is fx equals to 2. That means any point on the line, any point along this line, if you draw a tangent line, it will be a horizontal line. That means slope will always be 0. The next rule that we are going to generate is called the power rule. Given the original function fx equals x to the exponent n, then the slope of tangent, which is your f prime x, will be n times by x to the exponent n minus 1. Before we do the proof, we have to understand some pattern in terms of binomial factoring. So let's take a look. if I have a minus b, then my answer will be a minus b. If I have a squared minus b squared, which is difference of squares, that means a minus b times by a plus b. And if I have a cubed minus b cubed, that's called difference of squares. That's a minus b, a squared plus ab plus b squared. And when I have a to the exponent 4 minus b to the exponent 4, the factor will be a minus b. This can be developed by using the long division or syntactic division. So a cubed plus a squared b plus a b squared plus b cubed. And if I do a to the exponent 5 minus b to the exponent 5, you have a minus b again, and you have a fourth plus a cubed b plus a squared b squared plus a b cubed plus b to the power 4. As you can see here, there is a pattern. They always have a minus b as the first bracket. This is being derived from the factor theorem. And next, there is a second bracket there, and there is a pattern in the second bracket. And this pattern is being developed by using a long division or the syntactic division. Now let's take a look. What's the pattern in the second bracket? So let's start with the second line. There's an a squared, so I have a to the exponent 1 and a to the exponent 0. And b squared, so then I start with a b to the exponent 1 and going backwards, b to the exponent 0. The third line, I have a to the exponent 3. Then I start with the a squared, a to the exponent 1 and a to the exponent 0. That's why you don't see the a. And b to the power 3 here. So the other end, b squared, b to the exponent 1, and b to the exponent 0. So there is no b there. So the fourth line, now I have a to the exponent 4. So I start with the a cubed and a squared and a to the exponent 1 and a to the exponent 0. And b to the power 4, the other end we will have b3, b2, b1, b0. So that's derived a general formula for factoring the binomials. If I have a to the exponent n minus b to the exponent n, the first bracket will be a minus b. And the second bracket will become a to the exponent n minus 1, right? Plus a to the exponent n minus 2 with a b now. Plus a to the exponent n minus 3, b squared. But we don't know how many terms are there, so we say plus dot, dot, dot. 3 dots means and so on. And that's fill in the last one. So b to the exponent n minus 1. And the second last term will be b to the exponent n minus 2 with an a. And that's our general formula for factoring a binomial. Now, let's prove our power rule. Slope of tangent, which is f prime, equals the limit. H is approaching to 0, f of x plus h minus fx divided by h. And let's find what's f of x plus h on the side. We know fx equals x to the exponent n. So f of x plus h will be x plus h whole thing to the exponent n. Now let's substitute into the first principle. Limit h is approaching to 0, x plus h to the exponent n minus x to the exponent n divided by h. And now we're going to use the factoring skills to factor out the numerator. So the numerator is a to the exponent n minus b to the exponent n divided by h. So our factor will be a minus b and a to the exponent n minus 1 plus a to the exponent n minus 2 times by b plus a to the exponent n minus 3 times b squared plus and so on plus b to the exponent n minus 1. And the whole thing divided by h. And as you can see here, your a is x plus h, and your b is x. So that's x plus h minus x plus h, n minus 1 plus x plus h, n minus 2 times x plus h, n minus 3 x squared plus and so on, plus x to the power n minus 1. Now, let's simplify the numerator. The first bracket, you have x plus h minus x. So x can minus the x, so now we only have h left in the first bracket. And we just copy down the entire second bracket. Next, let's simplify it further. Now, you can see we can simplify this line by using the exponent law. When you are multiplying powers, then you add the exponents together. Next, you see they have a common factor h in numerator and denominator, so we can factor this, and please remember to write down restrictions. H cannot be 0. Now, since the h in the denominator has been divided into the numerator, therefore we can put 0 into h to calculate the rest of the function because the denominator is not 0. And once you put 0 into the h, do not write limits anymore. So now we know if your fx is x to the exponent n, then your differentiation, which is slope of tangent, will be n times x to the exponent n minus 1. And this is the power rule. Then we can simplify the line to this. Plus 1, because that's exponent 1 here. Plus 2, because that's exponent 2 here. Now, let's simplify all the exponents, and you will see they all have n minus 1 as exponent. And there are in total n terms. Therefore, we can write n times x to the exponent n minus 1. Now, let's use the differentiation rules to differentiate the following functions. Before we can use the power rules, we need to make sure there is no fractions, there are no radicals. So first thing is we have to change every single term into the exponential form. So for example 1, part A, we have fx equals x to the exponent 6 plus 3x squared plus x to the exponent 5 over 3 minus 5 times by x to the exponent 1 over 2 plus 2 times by x to the exponent negative 1. And now we differentiate f prime x. So bring down exponent 6, x to the exponent 6 minus 1. Plus 3, bracket, bring down exponent 2, exponent take away 1. Plus, bring down exponent 5 over 3, x to the exponent 5 over 3 minus 1. Minus 5, bring down exponent half, x to the exponent half minus 1. Plus 2, bring down exponent negative 1, x to the exponent negative 1 minus 1. Now, let's simplify it. F prime x will be 6 times x to the exponent 5 plus 6x to the exponent 1 plus 5 over 3 x to the exponent 2 over 3 minus 5 over 2 x to the exponent negative 1 over 2 minus 2 x to the exponent negative 2. Final step, we are going to remove all the negative exponents by bringing them down to the denominator. So I will have minus 5 over 2 x to the exponent 1 over 2 minus 2 over x squared. And that will be it. For part B, you see a perfect square. The first thing you have to do is you have to expand it. You need to have individual terms before we can use the power rule. So we will have 4x squared minus 6x minus 6x plus 9. That's simplified then. You get 4x squared minus 12x plus 9. And then we're going to differentiate it. So y prime, which is 4 times, bring down exponent 2, x to the exponent 2 minus 1, minus 12, bring down exponent, which is 1, x to the exponent 1 minus 1, and 9 is a constant, so it becomes 0. And we simplified it, so you get 4 times by 2 is 8, x to the exponent 1, minus 12, x to the exponent 0, plus 0, and anything to the exponent 0 is 1. So minus 12 times by 1. So your differentiation will be 8x minus 12.